So, hi everyone. Today was our latest IYCN Science Café. Today we're going to talk about nanoparticle megalibraries together with Dr. Peter Smith. Thanks, Dr. Peter, for accepting our invitation and for giving us a brief introduction and an overview about your work about nanoparticle megalibraries. So, first of all, I would like to present myself. My name is Walid Hiba. I am the IYCN's Conference Presence Committee Co-Chair, together with Tracy Lowe.
Thanks, Walid. Hi, everyone. My name is Tracy Lowe. I am the other co-chair of the Conference Presence Committee. I'm going to pass it over to my colleague, Elisa.
Thanks, Tracy. Hi, everyone. My name is Elisa. I am a researcher at the University of Coimbra, Portugal, and member of the International Younger Chemists Network. I'm very pleased to co-organize this event, and I take the opportunity to thank Dr. Smith for accepting our invitation and also the audience for joining us today. Thank you.
Okay. And we have a fourth member from our committee. His name is Samuel. Great to have you with us, Samuel. So the outline of the Science Cafe will be like a 5 minutes introduction about who we are, followed by like 25 to 30 minutes presentation by Dr. Peter Smith, and then we have like 20 minutes Q&A session, and after that we'll have a closing remarks. So without further ado, who we are? We are the International Younger Chemists Network. We are an associate organization of the IUPAC since 2017. Our vision is to connect and empower younger chemists globally, and our mission is to support and advocate younger chemists across the chemical sciences toward a globally sustainable future. So if anyone is interested in joining us, you can join us through this link, www.iycnglobal.com/membership, and you can follow us on all social media platforms from LinkedIn to Facebook, Twitter, or Instagram. Finally, this is a photo from our delegates attending the first IYCN General Assembly in Paris in 2019. So a brief introduction about our speaker, Dr. Peter Smith. Just a minute. Okay, so Dr. Peter Smith is the Wimberg Postdoctoral Fellow at the University of Northwestern University and the International Institute for Nanotechnology, working with Professor Chad Merkin. He earned his Bachelor of Science from New York University and his PhD from University of San Francisco, Berkeley, with Professor Christopher Chang in 2020. His graduate work revolved around supermolecular platform, electrochemical reduction of carbon dioxide and oxygen, and multiple other subjects. His research in Dr. Merkin's lab focuses on nanoparticle megalibrary synthesis methods and solving challenges in high put through catalyst discovery using molecular sensing. So without further ado, Dr. Peter, the floor is yours.
Okay, great. Yes, thank you again for inviting me, for attending. As was said, I'm Peter Smith. I'm a postdoc researcher in Chad Merkin's lab at Northwestern University. And so today I'll give an overview on our work on using nanomaterial megalibraries, and in particular looking at how we synthesize them and how we then use them to discover new materials. And so as chemists, when we're trying to make new things, we have different scales of, I guess, chemicals that we can work with, all the way from bulk materials on the left, going to the nanoscale, shrinking down further to single atoms, or working more with molecules and enzymes. And so for specific applications, whether it's biological or catalysis or synthesis, we sort of need to choose a scale in which we're working at. And then beyond just the scale at which we're working at, we need to look at the elements of interest. What elements are we actually going to be putting into these materials and working with? And so it's quite a lot of choices that you can make. And so if you look at how we approach this question, really the most of the applications and most of the synthesis is instructed by empirical observation. So we look at what people have done in the past and see how can we make slight changes to make things a little bit better. But really, at this point, we sort of don't want to be limited by empirical observation. We sort of just want to be able to make anything that we can possibly imagine be mainly limited by just the elements on the periodic table. Can we just choose something on the periodic table, make something out of it, and see if that'll have some advantage for whatever application that we're interested in. And so that's the ideal, but it sort of makes the challenge even greater. And so as an example, if we just look at nanomaterials in particular, just the types of nanomaterials that you can make is immense. So just some parameters that are important in terms of nanomaterial synthesis, whether it's composition, size, the shape, phase, or structuring. You can see there's quite a variety of different structures you can obtain. And just to look at some numbers, if you're thinking about like a metallic nanoparticle, we have 61 metals with stable isotopes that we can sort of put together. And if you go up to mixing 7 elements together, you already have 10 to the 8th possible combinations. And so if you then take that and start introducing size changes, so 1 nanometer size changes, you're jumping up to 10 to the 10th possible compositions. Then also now changing the ratio among those elements, you're expanding all the way to 10 to the 14th. So it's a scale of materials design that's really not accessible by traditional methods. And so what we're trying to do is make methods that will make it a little bit more accessible to probe this design space more easily. And so if we think about traditional chemistry experimentation in the lab, we're doing a lot of stuff in round bottom glass or small vials. We can now parallelize this, and a lot of us have probably used 96 well plates. So now doing this type of parallel experimentation, shrinking the volume down so you can do more reactions at the same time. And so what we're doing in the Merkin group is sort of pushing this to the extremes. And that's what this Megalibrary is, where we have these chips, which are just 2 by 2 centimeter chips that you can hold in your hand. And if you zoom in, you have these reactors or these wells, where now each of these droplets is a volume of 10 to the minus 14. So really shrinking it down from the 0.1 milliliter scale. And because of this small volume, this small size, we can now put over 100 million of them in this centimeter size chip. And so we now have this method of making these huge arrays. And so what can we actually do inside of them? Well, we can do material synthesis. So these SEM images are showing a particle synthesis inside of these reactors. And the main advantage is that we have this really small volume, which enforces formation of a single particle. And so that's really advantageous here. And so the history of how we've come across Megalibraries really spans the past 25 years in the Merkin group, where we've taken concepts of serial and parallel printing that we see in the macro scale and just shrinking it down to the nanoscale. So it started with dip pen nanolithography, so you can use nanoscale AFM tips to draw molecules on the surface. And then over the past years, parallelizing it so you can use more pen tips at a time, changing the types of molecules or materials that you're patterning onto the surface, or changing the energy inputs that you use to make materials. And so now we're at a stage where we can move beyond synthesis and try and do types of new discoveries using this platform. So more specifics on how or what this actually looks like. So we first use just standard lithography techniques with silicon wafers and sort of elastomers coating onto it, so we can construct these arrays of pen tips. And so you can see the wafer scale, we can generate large amounts of pen tips, and then zooming in, you can see each one is a pyramidal shaped pen where the tip is now at the tens of nanometers dimensions. And so in this video, you can see what it looks like when we're actually patterning on a surface. So each of these squares is a pen tip, and we're viewing from above as we're going up and down and touching on the surface. And see the light changes when the tips are touching the surface and they're being slightly deformed. And as they're touching the surface, they're transferring molecules from the tip to the surface. And so if you do this patterning in just under 30 minutes, you can now generate a Megalibrary where we have this centimeter-sized array with, in this case, over 200 million features of these droplets. And so going back to the synthesis that we're doing inside of here, this technique is called scanning probe block copolymer lithography, we're patterning on the surface these droplets, which contain this block copolymer shown here. So it has PEG and pyridine moieties on it. And then in that, we dissolve metal atoms that will then sort of use this polymer as the solvent as we heat up the reaction. And over time, the metal atoms will reduce, aggregate, and form a single particle, as you can see in the video of the in situ particle formation result. And so with this SPBCL technique, what we have now is very precise position control of each of these nanoparticles. We can change the size of the nanoparticles pretty easily by just changing the volume of the reactors that we're using. And then we have very high composition control because what we're putting into the nanoreactors will all end up in the final product. So we can put in this figure showing up to 7 different or 5 different elements that are all then coalesce into single particles and get these very complex heterostructures that are very difficult to attain by other synthetic means. And so we've expanded this type of nanoreactor synthesis to other types of materials, but all taking advantage of this very small volume confinement method. So in this case, we're making halide perovskite nanocrystals, where we do the same idea of putting inks onto the pen tip, so just these molecule precursors, patterning them on the surface. And in this case, the nanoreactor is instead of a polymer, it's a volatile solvent. So over just a couple of minutes, it'll evaporate. And as it evaporates, the perovskite precursors will crystallize into single crystals. And so you can see images again showing arrays of these perovskites. We can tune the composition by putting in different anions or cations, and then we can also pattern multiple materials on a same substrate. So in this case, sorting, we can construct like an RGB array of perovskites. And so what we have at this point is a very powerful synthesis tool to do nanocombinatorics. So we can make lots of unique structures, putting in lots of different elements into the design. And so what we're now moving forward is what we can actually do. Can we generate these libraries and explore new applications? So, and in particular, very interested in challenges in green chemistry. So using renewable energy inputs to sort of drive new reactivity. Okay, so one of the first examples in using megalibraries for materials discovery here, I'll focus on a perovskite example. So for doing high throughput screening, we now need to tune lots of different compositions of the perovskite in a single array. And so what we can do is pattern a library where every perovskite particle is identical, and then go through with a laser and shine the laser at each individual crystal one at a time, just for just a couple of seconds. And as you shine the laser, you induce loss of some of the ions. So in this case, we're inducing loss of bromide ions. And then the extent of irradiation correlates with the extent of defect generation. And so after we introduce defects, we can then submerge the perovskites into, in this case, a chloride solution, and those chloride anions will now be introduced into the defect locations. And so you can see these optical images on the bottom after irradiating with the laser, where we see the defects are causing a loss in fluorescence. And as we introduce chloride, we sort of regenerate the fluorescence, but the extent of chloride now changes the color. And so we can use this to discover materials that have a good blue photoluminescence, so very important for making blue LEDs, for example. And so you can plot on the bottom right this wavelength versus intensity plot and sort of find which material has the highest intensity for blue emission. So now beyond this sort of serial generation of composition gradients, we're also exploring a lot of using parallel techniques to make composition gradients. And so what we're doing in this case is now creating the composition control on the pens before patterning. So we can take 2 different precursors, so in this case A and B, and spray them onto the pens. And so now we have from left to right a gradient of composition, and then also from top to bottom we have a gradient of the volume of ink that we're putting on the tips. And so now we can then pattern on the surface. And so you can see on this bottom left image, it's a pattern of nanoreactors containing red and blue dyes. And so you can see the color change for composition control. You can see the intensity change is the size control in the nanoreactors. And so in this example, we have over 120 compositions and sizes each. So it's over 15,000 combinations that we're making in parallel. Each one has 900 replicates. And so over 14 million total reactors. So it's a big increase in scale relative to the serial composition gradients, as with the perovskites, where that was just around 4,000 unique compositions. And now with here, we're up in the tens of thousands unique combinations. And so what we first did with this example is a first catalysis example of, can we use these libraries to discover materials that can catalyze the growth of carbon nanotubes, for example. And so what we did is we made a gold copper megalibrary on top of these pillars on a surface. And so the reason we're using these pillars is that we can shine each one individually with a laser, so that we can heat each pillar up to 600-700 degrees in complete isolation from adjacent nanoparticles. And then at the same time, use Raman spectroscopy to quantify the extent of carbon nanotube formation on each pillar. And so then we can screen across the gold copper design space and discover that a gold 3 copper composition has the highest activity for growing single-walled carbon nanotubes. And it's a composition that had not been discovered previously. And so now we're getting towards increasing the complexity of megalibraries even further. And so what we discovered is that we can take now any substrate. And so if we're thinking about functionality with megalibraries, the substrate is usually very important. So in the previous example, we needed to heat the substrate. In other examples, we need to apply electrical currents, or we need to have some light absorption activity in the substrate. And so we need to be able to expand the compatible substrates with the megalibrary synthesis, which is very surface sensitive. And so what we discovered is that we can take an arbitrary substrate, coat it with a polystyrene film, and do all of the lithography and particle formation on that polystyrene film. And then higher temperature treatment will just degrade the polystyrene and deposit the particles on your substrate of interest. And so now we have this universal coating that we can apply to anything and have a much more reliable megalibrary synthesis technique. And so you can sort of see here on the right, these patterns of gold nanoparticles on a very rough glassy carbon surface, or this nanoparticulate titania surface. So you can get now nanoparticles patterned on top of other nanoparticles. And so with this method, we can really push the limits of our composition and size control, where in this case, we're using that spray application technique on the pens, but we can do now 4 different sprays. And so we can spray any mixture of elements. In this bottom left example, we're spraying gold at the top 2 corners and then palladium and copper at the bottom 2 corners. And we can predict the design space that we're working with. So going up for like 91% gold, 1% palladium, 7.5% copper, for example, and sort of having every composition in between those, that design space. And so essentially, each pen tip is now coated with a unique composition. We have now 90,000 total compositions that we're patterning. And then if you look at a pattern created by one of those pen tips, we can now introduce size control in this patterning. So now each row is patterned at a slightly faster speed. And so as you pattern faster, the tip is in contact for a shorter period of time. And so you get these smaller nanoreactors. And then as you heat it up, each of those nanoreactors is converted into a nanoparticle. And so now we have, you can see the larger, about 35 nanometer particles at the top, and smaller, roughly 15 nanometer particles down at the bottom. And so in total now, with this 25 sizes, 90,000 compositions, we have over 2 million unique nanoparticles. And then each one has 25 replicates, so you have over 56 million in total. And so how do we then screen this for specific applications? In this case, we're looking at a photocatalysis example in which we're trying to use visible light to transform oxygen and water into reactive oxygen species. And so now these reactive oxygen species can be used for various examples, such as water purification. And so to measure the extent of ROS generation within a megalibrary, we designed this experiment where we can pattern nanoparticles on a surface and then coat it with a thin film of this rhodamine B molecule. And so as ROS are being generated, the ROS will react with the rhodamine B, degrade it, and cause a loss in fluorescence. And so if we pattern these 25 by 25 micron squares of nanoparticles, and then do this experiment, we can see on the right this uniform loss of fluorescence induced by the gold nanoparticles generating ROS. And so this proves that we can visualize ROS generation with micron resolution. And so then we applied it to a megalibrary. So can we discover a new composition? And so in this area of photocatalytic ROS generation, gold, palladium, and copper separately have shown lots of promise. And so we wanted to look at this trimetallic design space. So we made a library of gold, palladium, copper nanoparticles on a titania surface. And so we're looking at 90,000 compositions. And so you shine light on it with the rhodamine fluorophore as a coating, and then image the entire library here. And so you can then zoom in on regions of interest and then sort of compare the relative loss in fluorescence intensity. So we can see in this panel 1, it's much darker squares, so greater decay of fluorescence. So there's larger ROS generation compared to like in panel 4, where there's only a little bit loss of fluorescence. And so then we can use this and determine which composition had the highest ROS generation. We discovered this gold 53, palladium 38, copper 9 on titania, which we can then recreate and show that it's this alloyed structure. And so this is our promising discovery for photocatalytic ROS generation. And so beyond these examples, we're really trying to expand the utility of megalibraries for discovery in green energy. And so we've explored the hydrogen evolution reaction as well, trying to find new nanoparticles, discussed the carbon nanotubes, perovskites, and photocatalysis applications. And then a lot of future work that we're working on is doing discovery for the oxygen evolution reaction. And so as we move more towards energy storage, this reaction becomes much more important. And so with that, I'll just end thanking everyone that's been involved. It's been a lot of people over the past couple of decades that have contributed to this idea that we're ultimately at with megalibraries. And so yeah, all this work is done in the Chad Merkin lab at Northwestern. I want to again thank everyone here for the invitation, also for attending and listening. And so excited to now do the discussion. Thank you.
Dr. Smith, thank you very much for your wonderful talk and for sharing your creative research work about nanoparticle megalibraries. We are now moving to the Q&A session of the Science Café, and we have some questions from the audience. I hope there's enough time to answer them all. So the first question is, synthesis and screening are complementary. Do you think all the required screening tools are available right now?
No. So yeah, that's they're very complementary, but they can be approached separately. So you can do the synthesis, like a lot of our work so far has been mainly just synthesis. How can we increase the complexity and the scale of synthesis? But then you can argue you can synthesize lots of things. If you don't have a way to screen, then there's little utility there. But the screening becomes just as important. We need to be able to screen all of these materials. So yeah, definitely complementary challenges, but lots of work to do. But I think it's a very exciting challenge. How can you screen among potentially millions of materials in a reasonable amount of time? You don't want to be taking days to do one experiment. So yeah.
That's very interesting and very challenging. Before the synthesis of these materials, do you take advantage of design and modeling and computations to predict the results?
Yes, that is something that we are incorporating more at this stage, trying to use computations to sort of predict what to do, but then also have a feedback loop of doing a screening and then getting those results and putting that into computation. So yeah, so we have various works of one just doing like DFT, where if we discover something, can we do DFT to understand why is it actually a good material for whatever application it is. The other thing that we're working a lot on is sort of doing machine learning, where can we take the results, whether it's like catalytic activity or structural information in these nanoparticles, feed that into a machine learning algorithm and have it sort of understand the results better and tell us what to do next. And so we have a published example where we took all of the nanoparticle heterostructures that we've been able to make. So we have these complicated either 1, 2, or 3 interfacial structures, feeding that into machine learning and having it predict what elements should you use to design new interfacial nanoparticles. And so it was able to tell us if you put these, I think, 6 elements into a nanoparticle, they will either alloy or segregate in a certain way to make a single interface. And it was a very complicated design that would not be something that you would just intuit on your own. And we're trying to do the same thing for catalysis. Can we take these, like the photocatalysis results, put that into some computational method and tell us what elements should we look at next? So yeah, that's definitely something that we're trying to do more of.
Another question. Do you think that megalibraries of nanomaterials could speed up clean energy, for example?
Yes, that is the hope. Yeah, so I mean, we know we need to do or implement more clean energy. But if you look at what specific application in clean energy, a lot of it is catalysis. So you look at like fuel cells, you have one, how do you make like hydrogen to be used as a fuel cell? And then how do you actually sort of consume the hydrogen to release the energy? And so those are both catalysis reactions that we need to discover materials for. And so if we can sort of explore design spaces that no one has really ventured into and do it at a faster speed, we can start to discover new materials that are competitive with the state of the art and do it much faster than a traditional method. So yeah, that's the hope.
Once you have found a positive match, what do you do with that material?
Yeah, so there's a few things you can do. The first would be sort of trying to scale it up and do more traditional testing on it. So like for the photocatalysis example, we have these materials in a patterned array on a surface. And so we discovered the best one in that particular environment. And so we need to make sure that if we then transition that composition into a more practical device, is it still as active as we hope it was? And so in that example, what we would do is try and, can we replicate this synthesis of a gold, palladium, copper nanoparticle on titania on milligrams to gram scale instead of the single nanoparticle scale? So that's first, is the synthesis scale up challenge is pretty large. And then the next would be then applying that material to sort of a large scale application. So there would be, can we do large scale water purification with photocatalysis in this material? So yeah, definitely scaling it up and doing more traditional testing so that you can then compare it to literature results as well. And then the other thing that you can do when you have a positive hit in a megalibrary is then use that result to dictate the next megalibrary you make. Or you can like sort of zoom in on that composition space, make a more precise library, or start with that hit and maybe add in another element and see if that changes things a bit. So you can do multiple generations of library synthesis and screening and really try and optimize the activity.
Yeah, optimization is the key. So what is green synthesis of magnetite and copper oxide nanoparticles, and how do they take effect on microtubes and diabetics agents?
What is the synthesis? Is that what's asking?
The green synthesis of magnetite and copper oxide. It's a question from the audience.
Okay. So I think maybe they're talking about like the different types of oxides that we're making in the nanoreactors. So when we're heating up the nanoreactor, we have different routes that we can go. Usually we'll be heating under reductive environments, under hydrogen, and we'll get just the metallic structures. And so we'll get like a metallic copper, for example, and which is pretty unique because if you then expose it to air, the copper should be oxidized itself. But what we see is that we're using this organic nanoreactor to do synthesis, and we sort of try and decompose it at high temperature. And what that forms a lot of times is sort of a amorphous carbon shell around the nanoparticles. So we'll get a metallic copper that's protected by carbon. And so it's not oxidized when we expose it to air. Alternatively, though, we can do this thermal annealing under argon or under air and target the oxide. So trying to make copper oxide directly or making iron oxide nanoparticles directly within these nanoreactors. And so, yeah, so we have different routes to go there. We have some work also introducing like sulfur, trying to get metal sulfides as nanoparticle products. So it is a very tunable synthetic method.
Okay. How much time is it possible to save with these mega libraries?
Yeah. Sure. I'm hoping that it's a lot of time. So if we think about the each step of the synthesis. So first you choose what you want to make, what elements do you want to work with, and just make solutions of those materials. So just maybe 30 minutes of preparation work. And then you apply those materials onto your pens. And so then once you do that, the patterning can take anywhere from 30 minutes to 2 hours, depending on what you're doing. Most of the time it's around 30 minutes of patterning. And then the long step is, for most of these, for the nanoparticles in particular, it's the thermal annealing. So we usually put it in a furnace overnight so we can do high temperature treatment, make nanoparticles. And then the next step is the screening method. And so there's various methods. The photocatalysis that I discussed was just it's a parallel experiment, so we can do the catalysis of the entire library at the same time. So shining the whole library with light for 30 minutes. So catalysis is happening everywhere. And then do fluorescence microscopy. So the microscopy actually also took 30 minutes because it is a centimeter scale chip, and we're taking images that are only maybe a couple hundred microns in width. So it's like 3,000 images that you then stitch together. So that was the longest part. But that's pretty fast, doing everything in just an hour or so of screening. We have other techniques of doing like serial electrochemistry screening, where we can do electrochemical measurements at specific points of a library. So in like 500 micron droplets, doing electrochemistry and sort of scanning around the library. And so this would be a serial catalysis characterization method, where in that case it would take maybe a couple hours to do the screening data. And so overall it's maybe 2 days of work if you sort of condense everything together, for like getting information on thousands of compositions. So definitely, I think saves you a lot of time. I think, especially if you think about like photocatalysis and electrocatalysis, doing traditional experimentation there, you're usually most of the time doing one sample at a time. just making one material, testing that one material, and it takes a while. Maybe you can do, there's some like electrochemistry well plates that I've seen, in which case it's maybe like 20 to 30 reactions happening at a time. So yeah, we're really trying to scale things up and save us some time, because we can screen lots of materials and very quickly say, okay, this whole space is bad, so let's not even waste our time looking at those materials. Yeah, whereas if you're doing one experiment at a time, you spend a lot of effort to identify something that's not good, which I think we've probably all experienced before. So making things faster is the goal.
It's definitely much faster than doing one by one, right?
Right.
And what kind of materials or nanoparticles do you like the most? What are your favorite ones? Do you have?
Sure. Well, I think for me, I've mostly worked with gold nanoparticles, and so I think just the simplicity there is what I like the best. Much more reliable, easier to work with, very bright and colorful. So that's what I like.
And let's see if we have more questions. How do companies help to advance these materials research? Are there companies investing money on them? Or?
Yeah, so Chad Merkin actually started a company around this idea to try and expedite materials discovery. And so the main goal there is sort of working with other companies to identify challenges. So working with someone who says, we want to make a fuel cell, or we want to make a battery. We want to now make the materials better. Can we use the Megalibraries to screen the materials that we have, make small changes in terms of like composition or size or whatever, and do it faster than what the company could do on their own? And so, yeah, so just working with established companies on existing challenges, trying to complement their work, their ideas, but sort of speed things up, make their materials optimization better.
Another question, what is the range of applications? I think you already answered this question.
Yeah, I think it's whatever you can think of. Hopefully we're not limited by anything. If you can think of an application, hopefully we can think of a way to address it with this technique.
I think someone asked, what are the new developments in nanotechnology? If there are any others?
I mean, I think Megalibraries are the most interesting advancement right now. I mean, there's always wild things happening in nanotechnology. What I am seeing this relationship or sort of correlation of using nanotechnology to speed up other applications. So it's been used a ton in biological spaces to make advances there. And so using nanotechnology to solve green energy challenges, I think, is what we're seeing a lot of people working on now.
I think then the next question is related to it. The person asked, how can nanoparticles be used in biomedical applications?
So I mean, a lot of work in the Merkin lab is pursuing this as well, delivering nanoparticles into cells to be used as therapeutics. So there's a lot of work in, I would think, like photodynamic therapy, so delivering nanoparticles that can target like tumor cells, for example, and then using light to shine on those nanoparticles to then kill the tumor cells. So there's lots of applications for nanoparticles in biology. There is sort of a balance of, are the nanoparticles toxic, and does that sort of outweigh the benefits of using them as some type of therapeutic? But so I think there's trade-offs that people are working to solve.
Working on this, yeah, because you have to. They must be compatible with the biological environment and
Exactly.
so on. So that's much more difficult. Someone is typing another question. What are the future plans for this technology?
So I think the future plans are sort of continuing along the same general ideas of using this discovery platform for sort of sustainability challenges. So I'm particularly interested in like electric catalysis. Can we use this to discover fuel cell catalysts that I've mentioned before, catalysts for doing like carbon dioxide into fuel transformations, or doing like plastic degradation catalysts. So I think in the catalysis space, I think there's a lot of room to work. So.
Okay. Well, I think we are done. So, Dr. Smith, I would like to thank you again for your inspiring talk and for answering all of these questions. It was a pleasure to have you as our guest speaker today, and we all wish you all the best with your future research work. And I will now pass the word to my colleague Tracy. She has some things to say.
Great. Thank you so much, and thanks for all the questions.
Thank you so much again to Dr. Smith. It was very informational, especially for someone who didn't know much about it. It's interesting to see the uses of nanoparticles and the future that will very hopefully as well. Thank you so much for your presentation.
Great, thank you. Thank you for inviting me.
I'm just going to move on to a few closing statements. We have previous Science Cafe series that you can see on our YouTube channel. So if you subscribe to the IYCN YouTube channel and hit the notification bell, you will be alerted to newly uploaded videos in the future. There is another event coming up. It is the Global Conversation on Sustainability, which is a joint project by the International Younger Chemists Network and IUPAC, which launched in 2022. It aims to address the UN SDGs by raising awareness and encouraging global conversations among diverse stakeholders, including university scientists, governmental and non-governmental organizations, business entities, and the whole scientific community on sustainability. Join the conversation on the 25th of September at 10 a.m. Join the IYCN again with another event in the discussion between young scientists and policymakers as they develop a better world for future generations. The event will be on the 4th of October at 3 p.m. and you can register for free using this QR code. The IYCN is also proud to announce the first online international conference, which will take place on the 27th of October at 1 p.m. CEST. We are also accepting abstract submissions for early career chemists to do a 10-minute oral presentation on their work. The topics include anything covered by the IUPAC Top 10 Technologies from any year. Abstract submissions close on the 30th of September. Please feel free to register using the QR code and to submit an abstract. Lastly, the IYCN has a commitment to equity, diversity, and inclusion. A network such as the IYCN can only succeed if early career chemists from all nations have the opportunity to join, network, and participate. This platform is a constructive route of bridging international borders. I'd like to thank both the speaker, Dr. Smith, and all the audience for attending. Please follow the IYCN on all social media networks and check our website page for upcoming events. Thank you, everyone. Have a good evening or morning or whatever the time is where you are. Thank you.